Hi everyone, welcome back to Blue Planet Week 2. So happy Friday Eve everybody. And today we are talking about chemical oceanography. So we're going to be learning a little bit about what's in the ocean water that is not alive. So the non-living things. And we are going to talk mostly about ocean acidification because that is a big issue in today's environment. So we're going to be talking about that. And let me go ahead and share my screen with you all. Here is our opening slide as usual. And yesterday we talked about ocean engineering. So we had Rich Delgado come speak to us. And he works for the Marine Resource Center in Gulfport, Mississippi. And he came and talked to us about all of the different types of technologies and equipment that is used in the field in marine science. And so they talked about lots of different things like autonomous vehicles, right? So unmanned vehicles. And then they talked about remotely operated vehicles, so ROVs. And we got to learn a little bit about how those things work and what they look like and just like how what they're used for. So that was pretty cool. And so today we're going to be talking about chemical oceanography. So we have a recap of yesterday. So just a poll question for you as we begin. What does ROV stand for? So we talked about ROVs, we talked about AUVs and ASVs. So what does ROV stand for? Random oven vent, rectangular organic beacon, remote operated villain, remotely operated vehicle. What is your choice? All 100%, perfect. So all of you had said remotely operated vehicle, which is the correct answer. So it is tethered to the boat and controlled by somebody who is on the boat operating it. So great. And we have another question for you. What does CTD stand for? So we talked about CTDs and what they do. They have multiple different purposes. So you could say conductivity, temperature, or depth, Canada, Texas, Denmark, centrifuge, texture, dollar, conductivity, temperature, density, or I was not here yesterday. If you weren't here yesterday, don't feel afraid to select that answer. That'll help me kind of figure out just where you're at. Okay, so we had some variation. We have one person who wasn't here, so welcome. And we have split down the middle between conductivity, temperature, and depth, and conductivity, temperature, and density. So the D stands for depth. So it is going to be named after measurements of conductivity, temperature, and depth, but it is going to perform other tasks as well, such as looking at the clarity of the water, the turbidity, and then also the phytoplankton and nutrient levels that are in the water as well. Good. All right, so let's get started with our chemical oceanography lesson. So the Earth is mostly water, right? So 97% of the water in the world is ocean water. So that means that 97% of it is salt water. So what are the other percentages? Well, 2.15% of the water on Earth is frozen in glaciers and ice caps. And then 0.62% is in groundwater and soil moisture. So that is just, if you were to dig at the beach or something, or, digging a hole to China, that kind of thing, that concept when you're a kid, that's going to be your groundwater. So it's just in the ground and lots of living things and plants rely on that. And then 0.02% is in streams and lakes, and then 0.001% is water vapor in the atmosphere. And if you're from Mississippi, you might try to argue that because there's so much humidity here. But yeah, there's not that much fresh water on our planet. So 97% is going to be salt water. And so what does that mean? What does it mean to have salts in water? Are we specifically talking about table salt, like what you put on your French fries? No, so that is just one type of salt, I guess that would be in water. So salt water is going to be made up of several different things called ions. So we kind of have to start from the basics. So if I were to show you a picture of the periodic table, there would be 118 substances on it, where an atom possesses the same number of protons as electrons, leaving it with a neutral charge. So an element is going to be something that has a neutral charge. And so an atom is going to be the basic, smallest particulate, right, of matter. And an atom is going to have things like protons and then electrons and neutrons. And so the protons have a positive charge and the electrons have a negative charge. And so whenever those two equal each other, that's going to leave it in a balanced state. And so that balanced state is going to kind of just make it happy, right? Everything in the world, everything in nature wants to be balanced. And so all of our elements on the periodic table are going to be balanced with a neutral charge. I don't have a picture of the periodic table because there are 118 things on there and it is kind of overwhelming to look at, but it is important to know that some of them are man-made and some of them are naturally made. So just keep that in mind. So an ion is going to be any atom or molecule, which is going to be a combination of atoms that possesses a positive or negative charge. So how does it get that positive or negative charge? Well, it has either more protons than electrons or more electrons than protons. So ions with more electrons are going to have a negative charge. So if you have an ion that has more electrons than protons, it's going to have a negative charge. And it's going to be the opposite for protons. So if your ion has more protons than electrons, it's going to have a positive charge. And so that's usually represented by a little symbol in the upper right corner of your element or of your ion. And that representation will also have a number by it that will tell you how many of those things it has too much of. So if it doesn't have a number, that just means it's one. So this would be like one too many electrons or one too many protons. If it was -2, you know it has two more electrons than protons. And it would be +2, then it would be 2 more protons than electrons. So that's just kind of an easy way to understand what's happening if you were to look at a molecular formula. So this guy right here, this is Jimmy Neutron. And has anyone seen the TV show Jimmy Neutron? Go ahead and answer that for me, yes or no. This was a show that was on a lot when I was younger. So I just want to know what the answer is. Ooh, okay. So 4 of you said yes and 5 of you said no. Well, it's a pretty fun show. So Jimmy Neutron is this guy here, and he's kind of like a mad scientist, if you can't tell by the hair. But he works a lot with physics and chemistry. And the intro to his show is, I'm talking about him like he's a real person. Well, the intro to the show is this really cool illustration and just animation of like atoms and just the interaction between different types of atoms. And so this is an atom right here on his shirt. And that's why he's got such good fashion, because he's got atoms on him. So yeah, this is Jimmy and that's Adam. Nice to meet you, Adam. So what is in our seawater? So in our seawater, that 97%, right, of all the water on the planet, 96.5% is water and then 3.5% is dissolved substances. And so what do we mean by dissolved substances? We mean all of these different ions, the things that we were just talking about. What's an ion? Well, here are some examples. And so our water is going to be our H2O, right? So 2 hydrogen ions and an oxygen molecule, or an oxygen atom. And our ions are going to try to bond with each other to create a balanced state. So they're all in the ocean in different concentrations and different quantities. This symbol here means parts per thousand. And so your salinity, or how much salt you have in your water, is going to be measured by parts per thousand. So the way we usually describe that whenever we're teaching water quality to the younger kids is if we were to have something that had a salinity of 20 parts per thousand, then if we had 1,000 buckets of water, 20 of those buckets would be filled with salt rather than water, and then all the rest would just be water. So it's just kind of like a ratio that helps you understand what we are actually looking at. So chloride has a concentration of 19.2 parts per thousand. So 55% out of this 3.5% is chloride. So that's going to be more than half, right? So more than half of the dissolved substances in seawater is chloride. And then 30% of the dissolved substances is going to be sodium. So that leaves us with a concentration of 10.6 parts per thousand. And so these are just the major ones, right? There's tons of things that are dissolved in the ocean, but these are just the main ones. And so if you look at your chlorine ion here, chloride ion, you have a negative charge. So this means that it has 1 extra electron more than protons, right? And your sodium has 1 more proton than electrons. And so what's usually going to happen is these two would like to bond together, right? Because they want to be in that balanced state. So in order to get to that balanced state, they usually try to find a partner that has the opposite charge as them with an equal amount. So this is 1 negative, so it needs 1 positive in order to become happy. This is 2 negatives, so it needs 2 positives in order to become happy. So those ions are usually going to try to partner up with something that's going to directly complement it. And that's an important thing to think about and to keep in mind as we go on with our lesson. So, what about water? What is water? So water is a molecule consisting of 2 hydrogen atoms and 1 oxygen atom, leaving you with the molecular formula of H2O. So the 2 atoms are joined by a covalent bond, which is going to be the strongest chemical bond. So covalent bonds, are they connecting the hydrogen to the oxygen, or are they connecting the water molecules to each other? Which one? All right, we had 100% of you said the hydrogen atoms to the oxygen atom. That is correct. Yeah, so this is the strongest bond that we have out of all the bonds, and it is connecting our oxygen to our hydrogens. So this is going to be really difficult to break apart, right? So our hydrogens aren't really going to want to leave that oxygen, and that is going to be very different from our hydrogen bond here, which is connecting the water molecules to each other. So that's going to be a much weaker bond. And so basically that just means that our water molecules are going to be more prone to separating from each other than they are going to be from separating from itself, basically. So yeah, keep that in mind. So what about pH? We talk about ocean acidification. We just learned all about ions. And so what do ions have to do with pH? What do you think a pH of 11 is considered to be? Do you think a pH of 11 is considered to be acidic, neutral, or alkaline? We haven't quite talked about it yet, but go ahead and answer this for me, and we will go into more detail. All right, so a lot of you said alkaline or basic, which is correct. But what are we actually looking at when we're talking about pH? So the pH actually stands for potential hydrogen. So what we're looking at is the amount of hydrogen ions in a solution. So it's going to be measured on a scale of 0 to 14. And then the first 7 are going to be your more acidic solutions, and then your latter 7 are going to be the more alkaline solutions or the more basic solutions. And so what makes something acidic? Having more hydrogen ions, H+, right, than hydroxyl ions. So in the pH, you are going to be looking at those two things. You're going to be looking at hydrogen ions and hydroxyl ions. So if you have more hydrogen ions, you're going to have an acidic solution. And if you have more hydroxyl ions, you're going to have an alkaline or a basic solution. But if you have equal parts of those two things, of those two ions, you are going to have a neutral solution with a pH of 7. So a neutral pH is going to be a solution like distilled water. So distilled water has a neutral pH. It's got an equal amount of hydrogen ions and hydroxyl ions. Ocean water is going to be slightly alkaline. It's got a pH of about 8.1. What is important to know, there's a lot of important things to know here, but one important thing to know is that the pH of the ocean used to be about 8.25. So it was more alkaline than it is now. And a lot of that is believed to be attributed to the Industrial Revolution. So as soon as we started burning more fossil fuels and creating more CO2, all of that was absorbed into the ocean and it dropped the pH. You may be thinking, why does that matter if you only went from 8.2 to 8.1? Well, it's because pH is logarithmic. So each number change is going to be 10 times the change of hydrogen ions in the solution. So if you were to move from a pH of 8 to 7, that is 10 times the number of hydrogen ions. And if you were to go from 8 to 6, that's 10 times 10. Wake up, mouse. My mouse is sleeping. So if you were to go from 8 to 7, that's 10. And then it would be 10 times 10 if you were to move 2 spaces. So that's 100 times the difference. So that is a very, very, very big change in your overall acidity or alkalinity of a specific solution. So why do we care? Why do we care that the ocean's acidification is changing, and how is that going to affect us? So we know in order for something to become more acidic, there has to be an increase of hydrogen ions. So where are all of these hydrogen ions coming from? And let's look at that just in the formula. So what's happening is we are interfering with the carbonate system, and that is what is having a huge impact on ocean acidification. So our hydrogen ions, if you look back chemically and through the chemical processes, it's actually coming from the increase of CO2 into the ocean. So if you remember in our physical oceanography lesson, we talked about how the ocean and the atmosphere work together to exchange gases and exchange pretty much energy, right? And so we talked about how oxygen from phytoplankton is going to come into the atmosphere, right? And that's what's going to be providing us with a lot of the air that we breathe, right? Or the oxygen that we breathe. So likewise, a lot of the CO2 that we emit is going to be absorbed back into the ocean. And so what happens with this influx of CO2 is this whole chain of reactions is altered. So usually when you get CO2, it combines with the water, and then you get carbonic acid. So if you look here, you know, you have, here's your 2 H's coming from your water molecule. Here's 3 O's because you had 1 O here and there's 2 here. And then you have your carbon. So your carbon dioxide and your water are combining together to create carbonic acid. And then usually that carbonic acid will split up into a bicarbonate and a hydrogen ion. And so this hydrogen ion can just be released into the air, or it can also kind of move over here to where we get 2 hydrogen ions together and a carbonate. So your carbonate is going to be just the CO2-3 here, or the CO3 with that -2 charge. And usually your carbonate is going to bond with calcium. That's what you want to happen. So the calcium is going to be coming from a lot of like the sand, and it's also just going to be found in the ocean, right? And so your calcium carbonate is going to be used to build all of these little shells, right? So our biological organisms are going to use the calcium carbonate to create their shells. But what's happening is we aren't getting this carbonate. A lot of our CO3 is going back to being bonded with that singular hydrogen and creating more bicarbonate. So we aren't creating an ocean that is going to be dissolving our shells necessarily. That is a common misconception. There would have to be more of a change in our pH in order to dissolve the shells. But what we really are doing is making it more difficult for those shells to get the materials that they need in order to be created. And so does this mean that you can't get into the ocean water because it's going to dissolve your skin or anything like that? No, but we are interfering with the chemical process that enables these shells to be created. So as we emit more CO2 into the atmosphere, this is going to keep happening. The ocean's going to keep absorbing a lot of it, and then we're going to keep altering this process. So ocean acidification is an increase in particulate CO2, which results in a lower pH, which means higher hydrogen ions, right? And a decrease in availability in our carbonate, and then a lower saturation state of the calcium carbonate. So there's literally just less of this molecule available for use. And that can be a huge problem because you have to think about all of the different organisms that are going to use that calcium carbonate, which is a lot more than just the 3 that you see on this image here. So this is just another depiction of the carbonate cycle, and you have your CO2 and your water, and then you get your carbonic acid and your hydrogen, your bicarbonate, and then you usually get this lovely little carbonate ion, and then your carbonate's going to bond with your calcium, get that nice balance going there, and then you get a calcium carbonate. And so this is going to be used by different types of mollusks, right? So pretty much any type of shellfish that you can think of. It's also going to be used by crabs. And a lot of people would argue that and say that crabs, since they're considered like arthropods, that they have a shell made of chitin, similar to insects. And that is true. So it is mostly made of chitin, but they do still need calcium carbonate in order to form their outer coverings, so, and their exoskeleton. So even the crabs need the calcium carbonate, not just the oysters and the scallops or the clams. Coral also needs calcium carbonate. So lots of things are going to be affected by this. This is from a YouTube video that I watched. I believe I have it linked on the next slide, but it goes into really good detail and explains this process really well. I didn't show it because it's like 12 minutes long, so I didn't want to, teach and have a 12-minute video, but it is available if you would like to watch it. So it's a really cool and very, very, very informative video. So who does this affect? Of course, our oysters, clams, snails, even plankton. So there is a type of plankton, type of phytoplankton called a coccolithophore. And a coccolithophore pretty much creates their single-celled organisms, right? But they can still do super cool things. So they create a shell out of calcium carbonate, and it just surrounds their single cell, right? And that they also, so they use that, and then they can also use, they release like a chemical into the water that has a really big relationship with cloud formation in the atmosphere, which is just wild to think about, that there's phytoplankton that is helping with the formation of clouds way up in the sky. So definitely research that if you would like to learn more about it. But there's also things like foraminiferans, which are going to use calcium carbonate to create their shells. And you will hear more about that tomorrow because those guys are important geologically speaking as well. It's also going to affect fish. So fish don't make shells, right? But the increased CO2 in the fish and also squids' body fluids can manipulate their immune responses. So how they're going to respond to sicknesses, disease, parasites, anything like that. And then it also interferes with their sensory mechanisms. So how does it do that? Well, it's going to change how they can detect prey based on their scent. So if you think about, you're changing the chemical dynamics of the water, that's going to be changing how things work through the water. So hearing is going to be affected as well. So like ear bones called statoliths can be formed incorrectly with an increase of CO2 in the water. And so that will interfere with balance and pressure detection in squids. So, oh, Louise is barking. But whales and other echolocating species are going to be affected as well. So changing the water chemistry can result in a change of acoustic properties. So that increased acidity is literally going to make sound travel through the water differently. And that is also going to be affected by other things like depth and just the temperature of the water as well. So all of these things that you can't see are going to have a direct effect on what's happening in the water. Fishermen, so your blue economy, right? Oysters and shellfish are going to be affected. And therefore people are going to have issues with their jobs, right? They may not be able to get their revenue if they are a fisherman, or if they work for restaurants, things like that. All these people are going to be affected by anything that drastically changes the ocean and what it does for us. So tourism as well, even if you don't work in anything related to the ocean, I'm sure you enjoy going to the beach and lots of people like to go out diving, right? And they look at all the coral reefs and everything like that. So all these things are very important to humankind. And so that is one of the huge reasons why we need to be addressing these issues. And so other than that, there's also plenty of other fascinating things to study in chemical oceanography. So if you see this image here, this is from the Deepwater Horizon oil spill. And so this happened when? I think we have a poll for that. Yeah, there it is. So when was the Deepwater Horizon oil spill tragedy? When did that happen? Fun fact, one of these days is my birthday. The month and the day, but not the year. When did Deepwater Horizon occur? Ooh, lots of different things. Somebody said the 4th of July. That wasn't it. Neither was May 12th or October 13th. It was on April 20th, 2010. So it has been 10 years. We just had the 10th year anniversary, I guess you could call it, of the Deepwater spill. And it affected lots of different things on the Gulf Coast. It got into the water, it can get into the sediment. So whenever people are taking geological samples, they can date all these things back, right? So if there was an oil spill years and years and years ago, they can usually tell that based on what's happening with the sand and just the layering, the stratification of the geology. So Deepwater Horizon also affected organisms, so it can build up in the tissues of your fish or anything that is living in the ocean. And then it also just got oil directly onto, like birds' feathers and things like that. So toxicology is something that you can study if you're interested in how these types of things, these man-made anthropogenic chemicals are affecting the wildlife or just marine species. And if you would like to look at how it is affecting their biological processes, because it directly affects like the reproductive system and their digestive system. And then it will pretty much affect generations after. So as it builds up in the tissues of those organisms, as they reproduce and have more organisms, those chemicals and things are going to be passed down. So pollution is also something else to study. So like watershed runoff, we talked a little bit about that in the biological lesson where we talked about the fertilizer and the dead zone. And then there's also biogeochemical cycling, which is going to be looking at how or like microbes are going to be working with chemicals and then also with like local geology. So those are some different things to study in chemical oceanography. So our speaker for today got his PhD in Earth and Environmental Science from Columbia University. He started working at USM in January of 2016. He studies isotope geochemistry, and today he'll be talking to us about mapping the invisible and trace elements in the global ocean. So he's going to talk at 3 o'clock, Dr. Chris Hayes, and he will be talking to us about all of these different things that are in the ocean, and not just the salt ions that we talked about before, but also like trace metals and things like that. So other elements, super cool. So if we have any questions, I will take those now. All right. Well, if we don't have any questions, we will see you back here at 3 o'clock to hear from Dr. Chris Hayes. So thank you all for joining me, and I look forward to seeing you again at 3. So please join us. All right. Bye, guys. Hi, everyone. Welcome back to session 2 of Blue Planet for our Thursday sessions. We talked a little bit about chemical oceanography and marine chemistry in our 1 o'clock session. So we talked mainly about ocean acidification and what that process is and kind of what it looks like, and just some of our basic ocean chemistry concepts. So thank you all for joining us. Let's see, we have Elijah here, Sadie, and Apollo, and our Denver student as well. Thanks, guys, for being here. So we have a couple of recap poll questions for you all, just to kind of figure out what you learned in that 1 o'clock session. So our first question is, what does pH stand for? Potential helium, probably hydrogen, or potential hydrogen? And the answer is potential hydrogen. Good job. Yeah, so we talked about pH, and it's measured on a scale, a logarithmic scale, between 0 and 14. Everywhere between 0 and 7 is considered acidic, and then 7 is neutral, and then 8 to 14 is going to be alkaline or a basic solution. And that's going to be the measurement of potential hydrogen. So what out of this list is the smallest? An atom, a molecule, a compound, or an element? An atom, good. Yeah, so an atom is going to be the smallest form of matter, and elements are going to also be atoms, but they're just going to have those balanced protons and electrons. But the most basic and the simplest form is just going to be an atom. Great. Yeah, so today we have with us Dr. Chris Hayes, who got his PhD from Columbia University, and he works over at Stennis with the Marine Science Department, and he's working in the marine chemistry section. And today he's going to be talking to us about mapping the invisible and trace elements in the ocean. So we're super excited to have Dr. Hayes with us today. And yeah, so we are ready to learn about what he has to teach us. So.
Okay, thanks, Galen. Get my presentation going here. All right, so hi, everybody. Hope you're having a good summer and ready to learn about trace elements. So yeah, you heard a little bit about me. If you're interested in what I'm talking about today, I have a website. You can go to chrishayesgeochemistry.com, or I'm also on Twitter. But I thought I'd start out with a little bit about my background, how I got into this field. So I grew up near the ocean. I always thought it was kind of a very fascinating thing. I didn't really start thinking about it scientifically until college, really. So before that, I was going through school, and in high school, I had a really inspiring chemistry teacher, who would give me extra assignments, and I just sort of got the idea that chemistry was a really cool way to look at the world, and thought I could do something with that in college and find a job. It seemed like a good skill to have. So then in college, I went for a chemistry major, and I was looking for something to apply that skill too. And, at first, maybe I thought a little bit about pharmaceuticals. It seemed like something you could get a job in, and that also helped people. But then, maybe my third year or so, climate change was something getting a lot of press, and there was things going on, and I learned that a lot of the issues around climate change involve chemistry, relating to the carbon cycle and other things. So in college, I decided I want to go into that field using chemistry to understand the earth and the ocean. And I also decided then that I just loved taking classes. I loved teaching classes and also doing research. And yeah, I just wanted to let you guys know that even if science sometimes seems something that's sort of tedious and dry, it's really a very creative activity, both for teaching and research. So in teaching, you sort of always have to figure out different ways to explain things and come up with new, interesting ways to get people excited. And in research, you're kind of figuring things out that no one has ever thought about before, and you have to design tests to figure out the problem you're working on. So it's a lot of fun what I get to do. So chemical oceanography, it's one branch of oceanography, but really all of the disciplines work together. When you have to go out on big ships like this, you end up knowing a little bit about everything. But to talk a little bit about what's specific for chemistry studies, I'll talk about some of the instruments that we use. So on the left here is this instrument that is called the rosette. So it has a CTD in the middle of it, if you've heard of that. It's basically a sensor that can measure the salinity, the temperature, and it can also do oxygen. And so you can measure things on a sensor, and it's lowered down with a wire. But surrounding that is the rosette of bottles. And these are called Niskin bottles. And this is basically a way for us to collect water out in the deep ocean from different depths in the ocean. So I would mention those sensors. There's some things we can measure with just sticking a sensor in the water, but for a lot of chemistry, looking at chemical elements and compounds, we don't have sensors yet. The technology just doesn't exist to be used in the field. So we actually have to collect some of the water and bring it back to land on a lab where we have the instruments. We may have to do some procedures in order to measure whatever chemical it is. So this rosette is really the main thing chemical oceanographers use to get water samples back in the lab. It's basically that ring of bottles. While it's lowered down, they're all open at the top and the bottom. So the water is flowing through it. And then when it gets to a certain depth, an electrical signal can be sent from the ship down the wire to close the bottle, the top and the bottom of the bottle. And then that bottle will have captured water from a particular depth. And working out in the deep ocean, it's like 3 miles down. So you can get water from all different depths to look at the structure of where the chemicals are, and that sort of helps you figure out what's happening. So there's a link here at the bottom that these pictures actually came from an expedition that happened a couple of years ago that I was involved with, that went all the way from Alaska, the North Pacific, to Tahiti in the South Pacific. And if you go to that website, there's all these posts about the research that they did and the interesting places and sampling and stuff we're working on. So I thought I'd talk a little bit about what I've done over my career. So to be a chemical oceanographer, you often go to sea a lot, in part just to be getting the samples that are way out there. So these are 4 different research vessels that I've worked on. I think I added it up, and I've been on something like 10 different expeditions and about half a year at sea, sort of spread out over about 10 years. Usually these trips are a couple of weeks to maybe a month is a sort of a longer one. But when I was pulling up these different ships I've worked on, one kind of cool thing to notice is just how different the color of the water is out in the ocean. So you can go from this really bright teal blue on the bottom right. That's a ship that works around Bermuda, and they have these really white sands there, and it makes the water that kind of light teal color. To the kind of dark electric blue on the bottom left, that is near Hawaii. And there you can get to really deep water that is very clear. And so that's sort of some of the clearest deep water will have that really dark blue color. And then on the top, you kind of get into these greens and browns and grays. You might also notice it's cloudy in those pictures, but those are also closer to some ports where, the bottom, the seafloor is really close to the top of the water. And so seeing the sediments on the bottom can change the color of the water. But anyway, this is just, different views of the ocean. It does really look different in different places. Okay, so yeah, these 2 ships I was on in the North Pacific. This one on the top is actually a German research vessel that we took from the North Island of Japan up into the Bering Sea, almost to the west coast of North America, and all the way back to South Korea. The ship on the bottom lives in Hawaii, and so we've done some trips around Hawaii there. But pulling up this Google Earth image is one kind of cool thing that, you can get to a part of the globe where almost everything you see is water. And the Pacific is really like that. It's just this amazingly large place. So those other 2 ships I worked in the North Atlantic on. So I mentioned Bermuda, that's sort of around the latitude of North Carolina, something like out here in the North Atlantic. And this other ship on the top is called the Nor, and it's actually kind of famous because it was the ship that was used to discover the wreck of the Titanic in the North Atlantic. And I got to take that on a trip from Portugal down to West Africa, all the way across to North America. And here in the North Atlantic, we'll get into this a little bit, but see the big Sahara Desert, and the winds actually blow a lot of this dust over the North Atlantic. And we'll talk a little bit more about that. So some of the questions chemical oceanographers work on, I talked about climate change, and really the big thing there is the carbon cycle. So we know carbon dioxide in the air is a greenhouse gas, it's trapping heat, and we've been burning fossil fuels that's significantly increased the amount of CO2 in the air. So some of that goes into the ocean, and it's causing an acidification effect, which you might have heard about. But really there's this big natural cycle of CO2 going from the ocean into the air, and we've just kind of amplified that a little bit. If you look at how much carbon is in the air versus in the water, there's actually something like 60 times more carbon dioxide in the water in the ocean than in the air. So the ocean is deeper, and it basically has a larger capacity to take up carbon. And so our burning of fossil fuels is sort of this little perturbation to that natural cycle, and figuring out the fluxes or the amounts of CO2 going in and out of the ocean is really important in order to predict things like how much CO2 in the future will get taken up by the ocean, or maybe there'll be less CO2 being taken up by the ocean. And so this is something chemical oceanographers really try to work out different parts of this cycle. So, you know, there's the part near the surface where CO2 is getting taken up, plants are growing, they take up the carbon dioxide and they make organic matter. And a lot of that organic matter sinks down to the bottom. And so that is this removal term. Some of it eventually gets buried in the sediments. So figuring out different parts of this cycle, like how much CO2 uptake is taken up by the plants at the top, how much is sinking down, how much gets totally removed out of the ocean, is the type of research questions that we look at. And I've been studying trace elements partly because trace elements are important for that biological productivity part, taking up CO2. So if you've ever had to work on an aquarium at home, you know, you feed fish, but if you actually look at the fish food, you know, it's not just the typical nutrients you think about: carbon, nitrogen, phosphorus, but there's all these trace elements and vitamins that are necessary. So we know we need iron, for example. We also need things like zinc and cobalt. If you've ever heard of vitamin B actually has a cobalt atom in it. You know, various things need iron, like the hemoglobin in our blood is red because there's iron in it. So the trace elements are essential for life, and understanding how they work in the ocean is also important in order to predict a bigger question like how much CO2 gets taken up in the ocean. So I'm part of this large research program that we are currently just mapping out where are these trace elements. So earlier in oceanography, they've done things like just map out where all the CO2 is, where the nitrogen and phosphorus is. The trace elements have only been studied later, you know, in our era, partly because they're more difficult to measure. They're much lower, you know, trace concentrations. So this map shows all these different expeditions that are going on to map out water and see where these trace elements are. So the ones in yellow are ones that have been completed. This one across the North Atlantic I mentioned that I used the NOR to do that study. And the ones in orange are still planned. So basically trying to cover the whole ocean. And if you're interested in this program, it's called GeoTraces. You could go to geotraces.org, where they talk a lot about these expeditions and what we're learning about it. So I'm going to show you a little bit of the data from this program in terms of the iron concentration. So that's an important trace element. And we'll see what we've learned from it. So hopefully you can see this video. And it takes a little while to orient your mental map of what's going on here. So this is basically the Atlantic Ocean. Africa is now at the top of the screen. There's Europe above that. North America is now kind of on the left. South America and Antarctica. That's land. You can see the shape of the seafloor in the gray colors there. And a big feature there is this giant mountain range that's at the bottom of the ocean. It's actually the longest mountain range on Earth. if you were to measure it from the top to the bottom, it's the tallest mountain range too. But that runs through the whole ocean, and in the Atlantic, we call that the Mid-Atlantic Ridge. And the color you see are these sections or cross sections where the ship went. And in some cases, you may see these little black dots, and that is where the CTD was dropped down and collected water at all these different depths. We're basically just trying to map out where the trace elements are. So the water itself mostly looks the same. It might have been a little bit different in color, but we're measuring something that's at a nanomolar concentration. So that's a very tiny concentration, something like 1 in a billion. And so we have to kind of make up a fake color in order to be able to see it. And that's why I call this mapping the invisible. Because we're mapping something out that you really can't see, but we know it's there at trace levels, and it's very important. So the the red colors are the high concentrations. And something we learned is that at that Mid-Atlantic Ridge, there are often these big clouds of iron coming out of what we call hydrothermal vents, which are places at the seafloor where the crust is kind of cracked and water gets down in and gets superheated by the hotter conditions below, and then that hot water gets shot back out as a vent in very hot water that has a lot of dissolved rocks, goes back into the water. And so we knew about those, but we didn't know how far the iron from the hydrothermal vents could actually travel away, and it influences the whole deep ocean iron distribution. So that was kind of a cool discovery. The other thing I'll point out, off the coast of West Africa, that Sahara Desert I pointed out, you can see much higher iron concentrations near the surface. And it turns out in the surface ocean, the blowing of desert dust from land actually is one of the major ways that iron gets out to sea. So we knew that rivers, carry some chemicals to the ocean, but in terms of iron, dust actually may be more important than the rivers. And so getting at the Saharan dust input and desert dust input in general is something I'm really interested in working on, trying to quantify that better. You might also notice down near Antarctica, there's much lower concentrations, and basically there's just not a lot of deserts in those areas. So there's less source of iron coming in. We'll go back to the presentation. So to recap and kind of put my some of my expeditions into that context, when we were working out in the North Pacific, one of the things we tried to do was to map out the effect of the dust in the northern China, Mongolia region. So the winds here actually can blow this across the North Pacific. And I made a map like this showing that dust from that region is blowing out over the North Pacific, even makes it to Hawaii. And that's basically what we had these stations to kind of map out that dust plume in the Pacific. And then back to the Sahara, the North Atlantic, just to sort of show you the surface map of where we think the dust is going. It has kind of a shape like this, and a lot of this actually gets to North America. And you may have heard about this in the news recently. So this happens seasonally, tends to happen more in the summer, a stronger dust plume. And in the summer, the plume can get further north. So it's actually much more common a little further south, say in Miami and the Caribbean, but it can get as far as the northern Gulf Coast. And right now, the plume is kind of having a further northern extent. So one consequence is that the Gulf of Mexico is getting more iron right now, so it's important for trace elements. For people, it's really not good to be breathing in a lot of that dust, so there's often air quality warnings, and if you have things like asthma, it can sort of not be good for you. But it's been a cool problem to work on. So enough about my research. I thought I'd talk a little bit about some of the other types of jobs you can get in the chemical oceanography field. So I talked a little bit about sensors, and if you're kind of a techie person that likes to build things, we have existing sensors for things like temperature, salinity, oxygen. There's many chemicals that we have no sensor for that we need to measure. But right now we have to do things like actually collect the water and bring it back in the lab. So there's always this development of sensors for new chemicals. A sensor for iron would be really cool. That's something they've been working on. And there's all types of other things you might be interested in developing sensors. And these are some companies that will sell the sensors to research labs or other people trying to do that work. There's a good amount of chemistry, lab work involved. So those are skills that can be applied in a lot of other places. You can be a lab technician on land, but if you like working at sea, you can actually be a lab technician at sea and kind of be on those research cruises all the time, both for private companies or public research, doing that kind of lab work. And you end up going to really interesting places around the world and all the different ports that you go to. So it's a possibility. So another thing you could use the chemistry skills for are the regulatory agencies. So, the EPA, NOAA does a little bit of this. Every state has their kind of own EPA type agency regulating their waters of basically how much pollution there can be. And, those people need to be scientifically well versed in, the chemical you're talking about and what the concentration limits are. You might think about what you could do to clean up a certain location, how to remove the pollutants. Those are types of things that a government agency might do. And then there's kind of the other side of that regulatory framework where chemical companies will actually hire consultants who are really well informed about the chemistry, the pollutants, and what the regulations are to basically help them meet the standards. So if what they need to do for the company is not meeting the standard in some way, they'll help figure out how they can change it to meet the standard. So, those two last ones, you're kind of doing the chemistry, but it's more office type work of writing reports and researching. So it's not only lab work that you would do with more of a chemical background. So a couple of final thoughts. I've talked about these research cruises, and it's a really cool thing to do if you ever get an opportunity. You may have to deal with seeing how seasick you get, but in terms of being motivated to find new things, it's a really cool experience. So when I was in high school, I had to read some other John Steinbeck books. I remember Grapes of Wrath, Of Mice and Men. But he actually wrote this other nonfiction book where he got to go on a research cruise into the Sea of Cortez, which is also called the Gulf of California, between Baja California and Mexico. And it's actually a little bit more of a biology cruise where they're looking at all the animals on the seafloor. But what's cool about the book is that you really get the sense and the feeling of what it's like to be there, where every day there's something new to look at, and you sort of try to figure out what's causing what you're seeing, and it's a really all-encompassing experience. So this is a cool book if you get a chance. And something else I'm into, I actually have created an app, cell phone app, to experience life in the deep sea. So we talk just a little bit about the chemistry, but biology kind of has the advantage in being able to show people really cool, charismatic creatures. The chemistry is this invisible world. We're dealing with these things that are, 1 in a million, 1 in a billion. We know they're important, but often the wild little animals can get more attention. So we've built this app that you can do just in a 2D mode on your phone. It also has a 360 mode, where if you've ever seen there's goggles that you can drop your phone into. There's cardboard ones you can get for something like $5, and you can do these undersea adventures, which they all have a little narration to go along with them. So it's called Dive in VR, and you could get it at diveinexperience.com, and you can get it for Apple or the Google Play Store. So that's all I had prepared for you guys, and I'm happy to stick around for any questions.
Thank you for your presentation. That was very good. Always love hearing about these things. Can you tell us how you designed the app?
Yeah, that's a good question. Sorry, I have somebody mowing their lawn outside my window if you're hearing that. But yeah, the app, I had to work with some software developers who actually write the code. But basically, once you have that set up, we searched for videos, and we got permission to use videos that was collected with 3D cameras underwater. So we had a couple different sources. One of them was from a research project that actually worked with the oil companies, and they let them put their cameras on the deep sea rigs that are out in the Gulf of Mexico, and the cameras would just see all these crazy animals coming up to the rig. So those are some pretty cool videos, and we also got them from some other sources, from people using submersibles. But we loaded in the videos, and we wrote the narration, and we got a couple different people to do the narration, and I did a couple of them, but we got some other people to do them as well.
So it's like local kind of stuff, like where were the oil rigs at?
Yeah, in the northern Gulf of Mexico, there's a lot of drilling going on. So people may have heard about the oil spill that happened in 2010. There's a lot of other locations in that area where it's kind of right where the seafloor starts to drop off really deep. So that's where some of it comes from. There's some from other locations, but.
Do we have any questions for Dr. Hayes? Let me check. I don't see any in the chat box, but I was wondering, we did talk about the oil spill a little bit in our 1 o'clock session. So do you see any effects or any traces of that in your work?
Yeah, that's a good question. I think it had some immediate effects in that the oil actually does have trace elements in it as well. And so, yeah, there were studies done really soon afterwards, and there were, because it was coming out so deep in the water, I think it affected a lot of the deeper waters. And yeah, it's hard to say what the longer term effects are now that a lot of the oil is sitting on the seafloor now. It still may be leaching trace elements. But so, yeah, it had an initial impact that kind of went away fairly quickly at the surface. But I think the longer term effects will be near the seafloor, which we'll still have to keep monitoring to see how that changes.
Do people in chemical oceanography work with that buildup in biological like organisms like mercury or like things like that?
Yeah, in the toxicology field, um, you would look into things like how much of certain elements causes a negative impact in the animals. So that's a little bit at the boundary of chemistry and biology, but yeah, mercury poisoning is a big one. One thing they've looked at is that in addition to the oil, they use this drilling mud, which when they're drilling a big hole in the seafloor, they need to fill it with something, or else the hole would just crack, collapse on itself.
Mm-hmm.
So they have to use all of this drilling mud, which tends to be barium sulfate because it has a good density for using at the seafloor. So there's some studies looking at possible poisoning from too much barium. It's also a type of heavy metal.
Wow. Where does that mud come from?
Well, the companies they make it. So sometimes they don't tell you exactly what's in it because they want to make it better than their competitors. But yeah, it has to be like a high density mud because you need something to sort of be sturdy to fill the hole. But yeah, they may have to mine the barium from somewhere. But yeah, it's an interesting thing to look into.
Right. Wow. I like never even would have thought of that. That's incredible. Any advice for our future oceanographers?
I'd say try to get out on the ocean, and even if it's just kind of on a recreational thing, once you start thinking about it scientifically, you'll probably notice a lot more things than you would have otherwise. So spending a lot more time on the ocean kind of generates the questions and what you might be interested about. So yeah, that's a big piece of advice. And another thing is just sort of to connect it to something that makes you motivated in your life. So for me, it was climate change was a compelling thing to work on. But there's other parts of, um, sectors in our economy and fishing and mineral mining, energy sector. So having some kind of tangible application of what you're learning also helps rather than treating it as just some kind of abstract concept.
Right. Oh, very good. Okay, well, I don't think we have any other questions. So thank you for joining us again for week 2. We really appreciate your time and all your effort and your presentation. And we will be back here tomorrow for our geological oceanography lesson for 1 o'clock. And then we will have Dr. Davin Wallace, who will be speaking at 3 o'clock on geology. So tune in for that if you are free at 1 tomorrow and free at 3. So join us. But yeah.
Okay, thank you.
Thank you. Bye, guys.